Hey everyone, this is a optimization problem. So we're going to use calculus to find the largest possible box that satisfies the following requirements. So we want the biggest box. Well, there's 1200 centimeters squares of material. So you have some material like cardboard, and that's our material to make the box, and it's fixed. So we don't get any more of that. And then, what else? The base of the box is a square. Let me draw a square over here, which I think we know, I think people know what a square is, right? So it's a rectangle and the four sides all the same length. So I'll assign X as the length of the four sides. That's a picture where we're looking above at the base of the box. Let's do a perspective drawing over here, which might not be so perfect, but here I have X, and X is the base of a box. All right, then, or is it all right? Let's see. Well, let me just sort of in a lighter color do the back part there. Okay, and then that's the base, and then I'm going to come over here and look at the height, and the height doesn't have to be X, the same length as X, is the same length as the side of our square. So I'm going to call that Y. And let's go ahead and do that. All right. Now the thing about this box is also it doesn't have a lid on top. So there's no lid on the top of that. In fact, I think I'm just going to get rid of that back one there. Okay. But there's no lid to this box. So got it? No lid to that box. And this is our requirement. And we're trying to find the dimensions I can make for X and Y, X by Y, that will give the maximum volume, given that the material is going to be 1200. And it's not like we're going to use 1200 and then like throw away pieces. So we're saying that that we have 1200, we're going to use all that material. And this one thing I can do, it's just maybe a little bit of waste of time, is I can try to indicate that I can do a little coloring in. So so that's a little bit fun, but maybe taking up too much time on this. So I could just keep going on and on, trying to draw the picture here even better and better. Okay, so look, I have this guy here, and I have some formulas that I'm going to write down. So my problem solving steps are, if you can draw a picture, do it. Maybe a graph, something or other like that. So I did a formula. Maybe I'll even improve upon those. Now, I'm going to write down the formula for volume. Now, volume is, for a box, is, you write down volume. Volume equals length times width times height. I said height, but I don't think that's how it's spelled. It's spelled height. It's a common pronunciation among math teachers, I've noticed, is they say height. But I believe the correct word is height. Hey, that's neither here nor there, but still. Okay, so in this situation, it's going to be X times Y. Or volume is X squared Y. For this particular box where the base is a square. All right, then a little more tricky is for us to understand what we mean by the area. Like, what formula will we get out of that? So for the area, what we want is we want to look at the base of the base of the box, which is a square. And we know that, hopefully, that the area of the square will be X times X, because it's a rectangle, and rectangle, the area is base times height. and then I multiply x times x, and I get x squared. Now notice I'm using base in two different ways, but I mean the base of the box being a rectangle. Okay, so the area of this square is the two dimensions x by x, multiplying and get x squared. Now, the thing about this guy here is that we have these sides, and the sides all have the same area, and that's just x times y. All right, because we're multiplying the two dimensions. Okay, so I'm going to add that 4 times though, and I think we can see that there's 4 sides, and I don't know, maybe that's hard to see, but there's 4 sides and a base. There's no top, so we don't have 2x squared, we just have x squared for the bottom, but no top. Okay, now, the thing about this though is that it's given though that a is fixed, it's 1200. So I'm going to write this as 1200, except it's sort of messy or cramped here. Oh, I'll just go with it. Okay. This is the base, and this is going to be the 4 sides. This is the sides. All right. So the area is 1200 centimeters squared, and that's equal x squared plus 4xy. So we have these formulas. I guess I'll highlight them, even though it's not like it's the final answer, but still, let's just highlight them, those two. And this is what we call a constraint. These are constraint problems. So we're trying to find a maximum value for the volume given the constraint that x squared plus 4xy is equal to 1200. Otherwise, if I'm trying to find the maximum volume, why don't I just make x and y super, super big? You know, and there would be no maximum. Just make them bigger and bigger. But there's a constraint. X squared plus 4xy equals 1200. Okay, on these constraint problems, the next step is that we eliminate one of the variables. And that sometimes is a little tricky for us to decide which one to eliminate, x or y. I will tell you that my inclination is to definitely avoid taking a square root when I'm eliminating a variable. So the first thing I have to do to eliminate a variable is I solve for one of the variables. And I am going to solve, am I going to solve for x? No, because then if I would have to take a square root. Actually, I'd have to use the quadratic formula. That's no way. So I'm going to solve for y. And so let's see, I have this in yellow, 1200 equals x squared plus 4xy. That's the 1200 is the amount of material we have is equal to the area of the base plus 4 times the area of each side. Okay, I'm going to write then 1200 minus x squared equals 4xy. Sort of, for whatever reason, I ended up writing it a certain way. Let me just write it. Let me use I think it's the reflexive property. I can flip that around. Now I'm going to solve for y. Okay, what am I doing throughout this? I'm solving for y. Well, I'm sort of talking away there. I'm solving for y. So first I add or subtract to get y, isolate y by itself, and then I'll divide by 4x on both sides to get y all by itself. Okay, so there's y all by itself. So I solve for y, and then I go back to the volume formula for which I'm trying to find volume. I'm trying to find x, y to make volume maximum, and I write volume equals x squared. Okay, and for y I put in 1200 minus x squared over 4x. See, I took that yellow formula above and I replaced y by y equals 1200 minus x squared over 4x. Now, okay, hold on. I need more paper. I need to add a page. All right, now a little bit of canceling goes on here. X squared and x. All right, got that. Volume is x now times 1200 minus x squared. Now it's still over 4. I'll still work on that. Okay, let me continue distributed property, x times 1200 is 1200x minus x squared, still all divided by 4. I'm going to, break this into two fractions. 1200 divided by 4, x minus x squared over 4. Now this is a quadratic, and I am partial to, for whatever, teaching pre-calc, to the idea of putting things in, in a nice form, which I would, did I do this wrong? Yes, sorry, but I'm that's not a quadratic. Okay, that's not even right at all. I don't know what I was trying to draw neatly or something that I got mixed up. But this is 1200x minus x squared times x, that's x cubed. Yeah, I didn't think there was a quadratic in this problem. I don't know. That's the thing, is that some people are better at avoiding little mistakes than others, but I make quite a few, and what I'm hoping, though, is I'll review. All right, I think that's it. Okay. And but if it isn't, I'll just make a new video, and then no one will know I made the mistake. Okay, so one more time. I think it looks good. All right. Now what I'm going to do is, I have this formula here. Let me just point out that this is not that clear, but x cubed, when x is when I have negative x cubed for x greater than 0, we'll find out. We'll see. I mean, actually, if you think about it, if you sketch the graph of negative x cubed over 4, as x greater than 0, that's a concave down function. And x doesn't have any concavity, 300x, because it's a straight line. But you add the no concave function plus the concave down function, and you're going to have a concave down function, which means that this function has a maximum, not a minimum. That's why I'm talking about this right now. I'm thinking, okay, does this even have a maximum? Well, the answer is yes. We're going to find that maximum. We're going to find where v prime is equal to 0, and I'm going to declare it's a maximum because I can tell because I know how to sketch the graph of negative x cubed over 4 that's that concave down. I'm not saying the graph looks like this, okay, but it looks something like that. But in the respect, or the idea that it's concave down. Okay, so now I'm going to find critical numbers. What are critical numbers? It's where the derivative's equal to 0, or where the derivative's undefined. But we're only going to get where the derivative is equal to 0 because this is a quadratic. But so why do I care about the derivative equaling 0? Because the derivative is equal to the tangent, the slope of the tangent line. Okay, derivative is equal to the slope of the tangent line. If the tangent line is slope 0, then the derivative is slope 0. And the tangent line is horizontal. And the tangent line horizontal corresponds to maximum values of a function. Alrighty, so let's continue on this. Derivative. All right, I have negative 1/4 times x cubed. I sort of think it would look better maybe if I have no problems with this, but maybe it'll be easier to see if I have negative 1/4 x cubed. I have the negative 1/4. It's the same thing as negative x cubed before. Negative 1/4, I take the derivative of x cubed, that's 3x squared. Then plus the derivative of 300x is 300. All right, I mean, it wasn't super difficult. And solve v prime equals 0. I don't think each of the pieces are difficult. I'm not saying it's easy. What I think is difficult is the overall setting everything up, and then, I'll show you, avoiding little mistakes here and there. Okay, I'm going to solve for x squared. And, okay, x squared will be, the two negatives cancel out on both sides. 4/3 times 300, so I multiply both sides by the reciprocal. So x squared equals 400. I see I have a perfect square, so because we're living in the world of Homer problems that come out to nice, easy numbers, I think I'm on the right track. In real life situations, I wouldn't think I'd get that, but anyway. Okay. Well, good to go here. I am not going to do a plus or minus. So x is greater than 0. No plus or minus. X is a dimension. So x is 20. All right, now that to me looks good enough. I'm convinced that 20 is x equals 20 is going to give a maximum value for volume. Because I talked about the volume function being concave down, so you can see from concave down function will have a maximum value. But there's another method which is sort of easy to use for this case, which is called the second derivative test. And what we do is we simply take it one more derivative of our function. And let's see, the first derivative is 4x squared plus 300. I'm going to take another derivative, which is one of the reasons I'm doing it is easy. If it were difficult to do, I'd probably figure out some other method. But I'm going to take this derivative and the second derivative now, and I'll just plug in 20, which is my critical number. And what do I get? Negative 30. Well, negative 30 is less, v double prime is less than 0. Why? What? Who cares? Well, I care because second derivative less than 0, v prime less than 0 means concave down. What? V is concave down. And that means, so x equals 20 gives a maximum value. What I mean is a local max, or it could be an absolute max, but it gives a maximum value. Because look, concave down. My horizontal tangent line is not super horizontal looking. Doesn't really quite look like a tangent line, but okay. Carry on. All right, for my class on the test, the second derivative test is optional. Actually, it's optional for me because I think I have other ways to argue that my result will be a maximum. Oh gosh, seems like I'm having trouble sometimes drawing little boxes. So I'm going to say that this part here is optional. When I do that, sometimes people say, well, you mean the whole problem's optional? No, I just mean that little piece. Okay, yeah, maybe I'll do that over here. Somehow, not the whole problem's optional. I'm just saying maybe when you're doing this problem, you don't have to do that part. Okay, we still don't want to do the problem. All right, so we can have x is equal to 20, and I think it's 20 centimeters. Let's go back to recall that. X is 20 centimeters. Now we're going to find y. How are we going to do that? I don't know if there's a ringing because of a text message or something, which is not mine, it's someone else's computer here. All right, we're going to find y, and what are we going to use? What we're going to do is use the constraint. The constraint said that 1200 equals x squared plus 4xy. Without looking above, I think that's it. I'm going to put in x squared is 20. And by the way, we already solved, we got that y is, we already solved for y in terms of x. Now I'm going to put, so maybe I should write down that formula. But anyway, I'm going back to our constraint. And I'm going to use that. Okay, so 1200 equals 400 plus 80y. And again, I have y equals 1200 minus x squared or 4x. That would probably be better. I mean, we could have used that. Okay, but this is sort of easy. 1200 minus 400 is 800 equals 80y. And then divide and we get 10 equals y. So y equals 10 centimeters. So interesting enough, the height for this problem is half the length of the dimension of the square base. Anyway, 10 is half of 20. It's easier to say it that right way. So the dimensions are 12 20 centimeters by 20 centimeters by 10 centimeters. And I drew the box that way to reflect that. I mean, that sort of shape. But it wasn't clear, but maybe it is. I mean, just intuitively clear that that's what would give the maximum volume. But I mean, all the possibilities are maybe you could have like sort of a short, flat one. I say, oh, maybe that's going to do it. Or maybe someone will say, no, I want to do a tall, thin box, and all using the same amount of material. But maybe intuitively people figure, no, that's not what it's going to do it. It's going to be a box where the height, we're talking about a box with a square base, where the height is 1/2, being 10 in this case, of sort of drawing and talking. Okay, the 10 is half of 20, so the height is half of that edge of the square base. So this is the one. This is their answer. This is the optimal. This is the optimal volume. These guys were sort of fun to draw, but this one here gives the optimal volume. So that's an optimization problem. Okay, and I just drew those little pictures just to point out that there were different possibilities. Now, could you have done that without calculus? Like you're in your garage and you're building this and you didn't do this calculus stuff. Would you have ended up with this? Maybe. That's an interesting thing. But all right. Okay, so review from the beginning or not? But let's just talk again. What's the problem? We have a box. It doesn't have a top. And the box has to have a square base. So I have x by x is the dimensions of the base. The side, or the height, I call y. It doesn't have to be the same as x. In the end, we found out it wasn't the same value as x. And what I'm doing is I'm saying that the amount of material is 1,200. So I find the area of the base. So here's my base. That's x squared. And then I find the area of one of the sides. They're all going to be the same, x, y. So we have the area of the base is x squared plus 4xy. That's the area. We're trying to find we're saying that's a formula for area, but I put in A is 1,200. So 1,200 is the area, and I have x squared plus 4xy. And then I'm trying to maximize the volume, which is, the volume is x times x times x. Okay, and then I I use this constraint to eliminate one of the variables. I eliminate y. I don't want to get rid of x because I have to take square root. So you solve for y, a lot of work. And finally, y is this 1,200 minus x squared or 4x. I replace y on the volume formula. Put it in there, and I put in for y, this guy y, I plug in this y formula in for volume where I see y, and I get volume is a function of x. Turns out to be a cubic polynomial. Then I take the derivative of that. That's a critical number. And why am I taking the derivative? I want to see where the tangent line's horizontal. Take the derivative and set the derivative equals 0. Turns out that wasn't super hard to solve, and I got that x is 20 feet. So that was good. And then I sort of wasted some time a little bit, but it wasn't that hard. Took another derivative to prove that at 20, v double prime is a negative number, so therefore v double prime at 20 is concave down, so that in fact the critical number has to be a max. And then easily I get y by going back to my constraint, plugging in x is 20 and get y. I mean, there's a bunch of little places to make mistakes. So saying easily is, I don't know why I started saying that, because none of this is easy, is it? Or is it, depending on who you are. But I think if you find this easy, good. That's super good. Become a math major. Wouldn't that be great? Or physics, engineering, build, they need to have something, spacecraft, when they go to Mars. Okay, you can work on that. That'd be super awesome. All right, so anyway, here's the answer, end of the video. That's all. Thanks. Goodbye.